Tonight, as we are extremely fortunate to have as our speaker Charlie Marcus. Charlie is a professor at the Niels Bohr Institute and the principal investigator of Microsoft Quantum Lab in Copenhagen. There, he also directs the Center for Quantum Devices. Charlie was raised even though he now lives in Copenhagen, he was raised in Sonoma, California, and studied at Stanford and Harvard. Before he went to Copenhagen in 2011, he also taught at Stanford and Harvard, so maybe there's a trend there. His research has covered a lot of grounds in the quantum physics of condensed matter. Right now, much of his research is focused on seeking condensed matter platforms for quantum information, as you will find out. And without further ado, please join me in welcoming Professor Charlie Marcus.
Thank you. Thank you for the kind introduction. Thank you for inviting me to give this talk. And thank you for hosting me in Aspen. This is the toughest audience you can give a talk to in the world. Why? How many people out here have an advanced degree in physics? You see the situation? You see them peppered into the audience waiting for me to say one thing that's not totally accurate so they can bust me either in person or tomorrow? So I want to tell you, all you people who put your hand up, this talk is not for you. You're not the intended audience. I didn't write this talk with you in mind. Hold your horses. The two pictures on the slide are, the one on the right is the inside of a nanofabrication facility that's used to make semiconductor electronics. The one on the left is a famous building. If you come and visit Copenhagen, if you have been there before, that's where Niels Bohr's office is. That's the famous Niels Bohr Institute, which is sitting just where it was, exactly as it was in those days. In fact, his office is still just how he left it. And it's open. You can come in and walk around. And the story of my talk tonight, while I'll try to get to the cutting edge, and maybe the part of the cutting edge, I'll give a little bit, to the people here with the advanced degrees in physics. Most of the story is about the journey from the building on the left to the building on the right, and what happened during the last 100 years of the subject. And so I hope you find it an interesting journey, and we'll end up with the subject of this week's conference in the Center for Physics. Well, it's been a remarkable event in technology for the last 70 years or so. In fact, in just one human lifetime, the world has been transformed by something that maybe even its inventors couldn't have anticipated, namely the invention of the transistor. And here, from 1947 to the modern day, is a revolution. The revolution, I don't need to tell you about it. You have it in your pocket. It's changed your lives. It's made you anxious about your children's development. It's made you anxious about your own development. It is revolutionizing every aspect of the nation, except possibly the microphone. If you look at the size scale here, this is spacing between lines of 120 nanometers, which puts these lines at something like maybe 50 or 100 atoms wide. The technology of nanofabrication has resulted in the ability to make transistors with billions of them per chip, and the crazy thing is, they all work. However, there's a finite capacity even with that technology. It's not that everything you dream of can happen. Why not? Well, here's the inside view of a data center. It's a pretty impressive picture. Those are racks and racks and racks of computer chips, each like the one that I showed, dense and fast, and the endpoint of something you've probably heard of called Moore's Law, where things get faster and faster every 18 months, the capacity doubles, etc. But I want to give you the answer to the question of what's the problem that we're trying to solve here by not looking at this fancy, beautiful picture, but by going down underneath the floor. What's that? Down underneath the floor is nothing but water. Water, 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 water flowing through that thing. Why? Because those transistors get hot. And keeping the system cool, keeping the system fed with electricity, keeping the carbon footprint of those data centers is, not to mention the cost, is a limiting factor in the technology that we live with today. We can't put enough of those chips together to do the problems that we need to have done. In fact, even when we do, we see, let's see if I can get this thing to go to its next slide. Yeah. So what you begin to see immediately is that the electric bill just to run these data centers, the carbon footprint of these data centers, is becoming something inexcusable and unaddressable by this technology. So what happens to all of the problems that are much, much harder than the problems that these things can solve? Build more, make them bigger, make them 10 times larger, 10 times taller, and 10 times deeper, and running on 1,000 times more electricity and putting out 1,000 times more carbon footprint? No, that's not the right way to get to the problems that are too hard for us to get to. We have to think of other ways of doing it. And so I want to take a new tack at understanding a way of computing that doesn't just take what we have and make it bigger and hotter and more expensive and using up more electricity and polluting the atmosphere more. I want to take a new look at the problem by going back 100 years and asking the question, what was bothering these guys? Look at their faces. They're bothered by something. And so I want to spend a little time asking, this is, you know the faces, right? This is Niels Bohr on the left and Albert Einstein on the right. And they were bothered by something, and this is what they were bothered by. If you look at any drop of oil on the surface of water, you see colors, and probably those of you who are interested enough in science to come to the lecture tonight probably took a science class in high school or college, and you probably learned how to figure out in that class what color was what on that sheet. Do you remember doing that problem? You would draw a little line, and you would figure out when the wavelengths would add up, and some of the wave would come down to the bottom of the oil, and some of it would go to the top of the oil, and when the wavelength just lined up for the red wavelength, it would turn red, and when it lined up for the green wavelength, it turned green, etc. You, and presumably the teacher, didn't bother with the question of when light gets to the surface and half of it goes down and bounces this way, and the other half goes down and bounces that way. Which half? What if I'm a little particle of light? Am I the lucky guy who gets to bounce off the surface, or am I the unlucky guy who has to go down and under the water? And who determines? This is part of what was bothering them. Let's take that same problem and turn it on its side, and just generally ask about waves. Here are water waves. I take a tub of water, and I stick my finger in, and I go like this in two places, and water waves ripple out. I think so far so good, I imagine, even for the people without advanced degrees. You can put your finger in water and watch those waves go. And you can even see places over here on the right where when it impinges upon the screen, it's got double the amplitude of one set of ripples. But here, in between those two, it seems to vanish. The wave adds up and disappears. You can do the same thing with light. You can let light shine from two holes, and by drawing the traces of those two lights, you can find places where the light will be twice as bright on the screen, and you can also find places where the light will be extinguished. Again, so far so good. Every wave you've ever seen does that, and nobody should be getting a headache about this kind of a phenomenon. Here's where the headache comes. The headache comes when we turn the intensity down, or we change it from electrons to photons, it doesn't matter, and we let the light go through those slits slowly, just very slowly. Just turn down the intensity and keep track of where the light lands on the screen. And what you'll see is the following. You'll see the pattern of light and dark, just like you saw from the two light sources that were shining on the screen. But that's after it's been built up for a little while. When it first starts to build up, it looks like these spots. Well, sure it does. These are the individual photons of light, or these are the individual electrons that are making their way onto the screen. But now you'll remember something that maybe will bother you. Wait a minute, when I did it with the light, didn't the light come from two different places? And now I'm letting the light go through the screen, like this. So what should I draw a picture like this where the light is made up of little balls? Well, that little ball didn't go through both slits to land on the screen. If I ask you about, let's take this one next to the letter B, that piece of light right there, and I say, where was that piece of light when it hit the screen? Well, that's not a hard question. It was right there. I could ask you, where was it right before it hit the screen? And you'd say, well, I presume it was on its way to the screen. It was just about right where it landed. Well, that wouldn't be right. What do you mean that wouldn't be right? Like an inch before it got to the screen, you're telling me it wasn't right about to hit the screen at that point? No, it wasn't there. Because when it got back to the part where it went through the two slits, it had to sample both slits and go in both places. That light wasn't anywhere. That light wasn't anywhere until it hit the screen. In fact, the way Bohr would answer the question of where was the light before it hit the screen is, you're not allowed to ask that question. That's not a good question. What do you mean asking the position of something whose position hasn't been measured? If its position hasn't been measured, it doesn't have a position. And that is what let it go through the two slits. If you didn't let it go through the two slits by having it have no position, you wouldn't eventually see the bright, dark, bright, dark. That's the problem. That's what was bothering Bohr and Einstein, and it continued throughout their lives. 1935, Einstein's most cited paper in the history of his literature. 1935. This is Einstein, an old man at this point. And yet he writes his most well-cited paper at this point, in which he drills down on this mystery. Writing a paper called Can Quantum Mechanical Description of Physical Reality Be Considered Complete, in which he concludes at the end of the abstract, one is thus led to conclude that the description of reality as given by the wave function, the waves of quantum probabilities, is not complete. Not wrong, but just not the whole story. Why not? What was bothering Einstein in 1935? It wasn't just the two slits. It was something much more profound than the two slits. It was something that got the name of the Einstein-Podolsky-Rosen paradox. I'll give you an abbreviated version of it here. Go out tonight. If the skies are clear, look at a star. That's all you have to do to be completely freaked out. Just look at the star. Why? Imagine the light is coming from the star. The light comes from some chemical reaction on the star, the electron falls down, and the light goes out like this in a wave. Now, what am I doing with my hands? I don't know exactly what I'm doing with my hands. I'm doing something with my hands that the light is coming out in waves. It's going toward me. It's going toward you. It's going toward the backside of the star, going 1,000,000 miles in the other direction. The light is coming out like this. Now, you remember that the light has no location. It's going out in all directions at the same time. Then, I open my eye. It lands on my retina. And I know how a retina works. A retina has to take the entire photon. The chemical reaction won't work unless the whole photon goes into my eye. So there it is. The photon is there. Well, wait a minute. I thought that photon could have been on the far side of the star, 1 billion light years in the other direction. Well, it could have been. In fact, there was a probability for it to be there. Until I chose to go out that night and open my eye and let the light go into my eye. And as soon as it hit my eye, it was there. And it wasn't on the far side of the star. So did somebody call out to the far side of the star? Sorry, he put his eye there, he caught the photon, it can't be on the far side of the star anymore. And if that's true, how long does it take for the signal to get to the far side of the star? To tell the photon that it can't be there anymore because Charlie went out and opened his eye and caught it in his eye. I made the photon disappear from the far side. This is crazy talk, right? The same year, 1935, Bohr, now also getting old, writes a response in a paper with the same title. Can quantum mechanical description of physical reality be considered complete? Those of you scientists out there, try doing that sometime. If your nemesis in the scientific world writes a paper that disagrees with you, write a paper disagreeing with the same title so you can share the references. Anyway, Bohr writes a response to Einstein's paper with the same title, 1935, in which he says, basically the response to this experiment that Einstein called out. That is, how did the thing vanish on the far side of the star with the message getting over there seemingly instantaneously? And, you could imagine the father of relativity not liking the idea that the message got to the far side of the star, if that's in fact what happened. That just sounds like a bad story if you say nothing propagates faster than the speed of light. Bohr's response is as follows. In fact, this new feature of natural philosophy means a radical revision of our attitude as regards physical reality. Whoa. I mean, he's not talking about physics anymore. He's saying our entire belief structure of how the universe works has been called into question by the idea that, yes, when I open my eye, I cause the probability to vanish on the far side of the star instantaneously. Don't like it? Go live in another universe. It was so jarring that for decades, right up to the present, there is a class of scientists who test this idea over and over and over again. And every time they do it, it comes out the same. Sorry, Einstein. Quantum studies suggest spooky action at a distance is real. So it doesn't matter whether you like it, and it doesn't matter whether Einstein liked it. All that matters is what happens in the experiment. And you have to get used to the idea that you're living in a world that's not quite the world that you thought you were living in. Bohr is famous for this quote. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So if there's anybody in here who is not in a state of shock right now, then I'll go back and do it again. Let's move to the modern age of electronics and take these same ideas with us. Namely, if I take something that looks almost like a two-slit experiment, except it's made out of a semiconductor and electrons can flow through it, if I give the electrons two paths to go to, and I do some other tricks like make it pretty small and I cool it down to low temperature, then I can get the kind of interference pattern that's very much like what is shining on the wall, where the electron must have gone via both paths, so that you know that this picture of an electron being here and there isn't quite right, because it's not really anywhere at the same time. It's kind of all over the circuit at the same time. How do I know it's all over the circuit all of the time and not just a blue ball? Because of the interference pattern, it must have been at some time in both places at the same time. That's the data that tells you about the interpretation. What that means is that if I take the electric circuit and run the electron through and say it's in both ways, electrons have this funny property. They carry charge. And charge can be used on the capacitor plate of a transistor to turn the transistor on and off. So now that I've said that the charge really isn't anywhere and it's kind of on this side and it's on that side at the same time, you must say that it must then turn that transistor on and kind of not turn it on at the same time. Well, that transistor lets electricity flow to some other part of the circuit and not let electricity flow at the same time, which then charges up and doesn't charge up another capacitor at the same time. It gets a little bit complicated. But this is quantum mechanics. This is the story of quantum mechanics, and it is a story that is not in conflict with any experiment. It is what a scientist would define as right. The way we say it is that the switch can be on and off at the same time, and this wave function with the Greek letter psi defines the state of the system as being composed of both parts together until the measurement occurs and then one of the outcomes obtains. That's the rules of the game. You can make the game a little bit more complicated by saying that the combination could be 80% up and 20% down. It doesn't need to be 50-50. In fact, the ratio can even carry some kind of complex number that represents phase. That gives the interference pattern. So you end up drawing not 80% up and 20% down, but all the possible vectors on the surface of a sphere, and you do the math as if that was the way it worked. 2 years ago, the Aspen lecture had a speaker named Scott Aronson. I was here for that lecture, and Scott Aronson is also famous for a particular quote. Maybe not as famous as Niels Bohr's, but Scott is famous for saying quantum mechanics is astonishingly simple, and I hope that you found those rules that I just told you very simple. It's 80% up, 20% down, or some complex phase up and down. You propagate the whole thing through, and when you get done, you make a measurement, and that becomes the outcome of a 0 or a 1 for the state that propagated through. As long as you don't think too much, everything's fine. Like the rules work, you get the right answers. And that is what Einstein was saying originally, which was, it's not that the theory's wrong, it just can't be complete. And yet, from that day to this, we've never found a better version of the story. We've never found an error with the predictions. And it seems, as much as anything we accept in our lives as being correct, this is correct. So now let's ask an interesting question. This is a question that maybe a physicist wouldn't ask, but an engineer would. Are there any engineers in the audience? Anyone professional engineers in the audience? So tell me if I capture the spirit of engineering correctly. I'm not an engineer myself, but you can nod or shake your head. You might even yourself be thinking, yeah, it's weird. It's kind of interesting. Is it good for anything? Is there anything you could do with that you couldn't do before? Let's ask. Is that a fair characterization? Yeah, he's shaking his head yes. So now I can turn on a transistor right here and not turn it on at the same time. It lets electricity flow to this transistor, turns on that transistor, this transistor turns on that transistor. In fact, it can even go back and turn on the original transistor again. The whole thing can propagate all around until finally I measure one of them. That determines the state of everything else on the chip. How fast? Instantaneously. Not even the time for light to propagate across the diameter of the chip. The state is determined instantaneously. What can we do with that? Let's ask the question, if we built a computer using these rules and take advantage of not measuring until we're late in the game, can anything happen that doesn't happen with a normal computer in which everything is either transistor on or transistor off? This is a theoretical question, and I'll give you 3 theoretical answers. The first one is in the subject of cryptography. And it arose from a famous paper that was published in 1996 on a public archive that read as follows. A digital computer is generally believed to be an efficient universal computing device. But this may not be true when quantum mechanics is taken into consideration. That is, it may be that there are quantum mechanics problems for which a computer is not an efficient tool. This paper considers a particular problem called factoring integers. Well, that's a nice little math problem that everybody in the room can participate in. I want all you scientists to shut your hands off for 1 second, and we're going to play a game for people who are moderately good at math, but not experts in math. A prime number is a number that can be divided only by 1 in itself, and I'm going to tell you that there are 2 prime numbers that multiply together to give you 15. Can you think of the 2 numbers? Yeah, shout it out. Non-experts, shout it out. 3 and 5, that's the correct answer. Okay, non-experts? 2 prime numbers multiply together to give you 4,633. Okay, I'll just tell you. The answer is 41 and 113. Now, what's interesting is, you couldn't see it, but I could see it from where I'm standing. when I flashed the second question up, nobody moved a muscle. Nobody reached for their calculators. You would know what to do with your calculator. So hey, go ahead, reach for your calculator. What are you going to do with it? What are you going to do to answer, not that question, to answer that question? What are you going to do with your calculator? You don't know. You just start guessing, but your calculator's not going to help you that much. Or maybe you multiply, maybe a little bit faster. And I'm telling you that it wasn't because you missed that day in class when they told you how to do that problem. That's just a hard problem. That's just a problem that computers do it with a little bit more efficiency, but they basically just start trying answers. So when I tell you that this top number is made up of the product of those two prime numbers, that little fact is the basis of internet security. It's the basis of encryption. It's the basis of that phone that the Department of Justice wants unlocked. All that stuff is all about that equation. Because whereas a computer can multiply those two numbers together very easily once it identifies your thumbprint, if it has that number, it can't do anything about it. And it can't figure out what those two roots are, just like you couldn't figure out what those two roots are. So what that paper in 1996 showed was, if there were a quantum computer in which this state determined that state, and this state determined that state, and everything propagated around the chip, that problem suddenly goes from being intractable, using the fastest known algorithm with 100 PCs at a clock speed determined by extrapolating to 2018. Once the number is 1,000 bits long, it takes the age of the universe to do the problem, using the fastest known classical algorithm. But if you have a quantum computer running at essentially any speed, the problem becomes easy, which means all of the encryption, all of the government secrets, all of the internet security is broken by one of these machines. That's interesting. That's an important problem. So it's not surprising that in 2019, finally, the US government, along with the European Commission in Europe, have dedicated, in the US, it's $1.3 billion to fund research to develop a quantum computer. Because the last thing we want to be is the second country to have one of these. It's okay if nobody's got one, but we don't want to be the second country to have one. So, it's an interesting time, both technologically and politically. Here's a second problem. I walked into the cafe that was before some of you were there, and this problem was being discussed. Here's an interesting, this is a picture of a maglev train, magnetically levitated train. It floats on a carpet of magnetic field. It doesn't have any wheels. It doesn't make any of those grinding noises because it's flying through the air on a magnetic field. The only difficulty is it needs a superconductor to make the currents that generate the magnetic field. Wouldn't it be fantastic if that superconductor were at room temperature? Is there a superconductor at room temperature? I see heads going in both directions. I'll give you my answer. I don't know. There's an interesting story about high temperature superconductors that conduct better than any metal. This one, magnesium diboride, has been around for 100 years. It's been sitting on chemists' shelves. It's just like sitting there. Turns out, some joker finally took it off the shelf and put it at low temperature. And lo and behold, one of the highest temperature superconductors found was sitting on a chemist's shelf for the last 100 years. How could nobody have known that? It's not that complicated of a molecule. It's magnesium diboride. Couldn't somebody have predicted that that was going to be a superconductor, not just a superconductor, but a high-temperature superconductor? No! There's not a computer on Earth that could have told you before you started. Now, let's say they did another trick. They said, well, okay, I'll tell you, I'll give you a hint, Mr. Computer. It's magnesium diboride. What's the transition temperature? No answer, says the computer. That's an unsolved problem. Here's another interesting problem. Did you know, I didn't, that we spend over 1% of our energy on Earth making fertilizer? Here's the breakdown in percentages. It's an expensive, energy-consuming, hot process that's very inefficient. But we need fertilizer. Without fertilizer, a lot of people's lives would be much less happy than they are now. Now, in most plants, or most legumes anyway, in the roots of those plants, there's a bacterium, and the bacterium makes fertilizer for the plant. It has a symbiotic relationship with the plant, and it makes the same fertilizer out of the air. It takes nitrogen, it fixes it into ammonia, and it makes fertilizer. It's complicated. It has to make, to take apart the N2 molecule and put it together to make ammonia. It's complicated. How does it do it? Well, there's a protein inside of the bacterium. In the heart of that protein, there's a little complex that has in it, interestingly, an atom of molybdenum. Molybdenum. I mean, you might not even know what the hell is molybdenum? It's also got an iron in there. Somewhere in there, there's an F somewhere. I can't see it. But anyway, and there's a carbon in the middle, and that little complex is the thing that rips apart the N2 and puts together the ammonia with the hydrogens to make the fertilizer. And it does it at room temperature, and it does it at very low cost. How does it work? Nobody knows. You don't believe me? Look it up. I'll look it up for you. Here, from Wikipedia. If Wikipedia doesn't know. Anyway, go read about this nitrogen fixation molecule, this protein that's in the roots of every plant, every legume. I'll read to you. The location of substrate attachment to the complex has not yet been elucidated. It is believed that the iron atom closest to the carbon, there's the carbon, to the interstitial carbon, participates in the substrate activation, but the terminal molybdenum is also a candidate for nitrogen fixation. That's it, right there. It's that big, and nobody knows how it works. Why not? Because it's too big for a computer to solve the problem of what happens when nitrogen comes into that molecule. Why molybdenum? Well, maybe that's just the way plants evolved. Maybe there's an even more efficient catalyst that we could put in that would make it even 10 times more efficient than plants. There's no reason to think that plants are, the best way to do it. But we have to understand what that thing is doing in order to understand what to do next. To make fertilizer without using 1% of the world's energy. So an interesting paper from colleagues in Switzerland and Microsoft and a large group of people have studied the particular problem of this, it's called a FOMOCO complex, for fixing nitrogen, and asked the question, if I wanted to make a quantum computer whose only job was to solve the problem of what are the excited and ground and chemical states of that molecule, how big of a quantum computer would I need? And their conclusion is that this can be formed in a reasonable time on a small quantum computer. It'll turn out you need 100 logical qubits. I'll come back to how you make that later. But it's not a hard problem if you have a quantum computer. And if you don't have a quantum computer, it's intractable. Last example that I want to give, and I'll move on quickly to what to do with it. This is from the Davos Symposium this last year. This study was published on December, so less than a month ago. The following article came out: How Quantum Computing Could Beat Climate Change. This particular article, so I'll just read to you because it's clear enough. At a meeting of the World Economic Forum's Global Futures Council last month, a team of experts from across industry, academia, and beyond assembled to discuss how quantum computing can help address global challenges as highlighted by the Sustainable Development Goals and climate in particular. There are known catalysts for carbon capture, but most of them contain expensive precious metals or are difficult or expensive to produce or deploy. Molybdenum, this metallo-organic, is an example of where a metal atom is used in an enzyme or as a catalyst. And we have catalysts that can capture carbon, that can remove carbon from the atmosphere. but they, like that molybdenum, involve precious metals. Given the infinite number of candidate molecules that are available, we are right to be optimistic that there is a catalyst, or indeed many, to be found that will do the job cheaply and easily. But finding such a catalyst is a daunting task without the ability to simulate the properties of candidate molecules. So there's a chemistry problem, folks, which is that once the molecule gets a little bit big, we're stuck. All those data warehouses are not going to solve that problem, but a modest-sized quantum computer will. Okay, well, I think I've motivated the problem. Let me ask somebody who's got a watch on. What time is it? 6:20. 6:12. And when would you like me to stop talking? 6:30. Okay. That's my goal. Let's build a quantum computer. Let's see how people are doing it out there. And then I'll tell you a cool idea for the last part of my talk about topology, the subject of this week's Aspen conference, which is maybe an interesting cut at how to solve this problem. Well, the approach is that you have to solve a certain difficult problem in technology. Here's the difficult problem. You have to be able to control every one of those bits that makes up the quantum computer. You have to open this valve, close this valve, do like your operating transistors. But you can't measure anything. You can't look at it. You have to do everything without knowing what anything is. Okay, sounds hard. So that you can't even think, how do I even write a program where I don't have to say, you could say, if you're a 1, oh, I can't do that. I can't say if you're a 1. I could say, if you're a 1, flip your bit. If you're not a 1, don't flip your bit. Okay, good. I don't know. I didn't say whether you were a 1 or not. I didn't measure you. I just said, if you're a 1, flip your bit. If you're not a 1, don't flip your bit. Is it possible to write all of computer code using this thing where you don't have to measure anything until the very end? Yes, it is. You can write general purpose computer code without performing measurements, only allowing all of the states to propagate at the same time. But in the lab, what we have to do is we have to make systems that can be manipulated, because you may or may not have to flip your bit. And you may have to do it in a nanosecond, depending on whether her bit is up or down. But you don't get to know until we run the algorithm. But I can't measure you accidentally. I can't even accidentally figure out what state you're in. Okay, so there's a couple of systems that people have been looking at. One of them involves atoms. And in the energy level of the atom, it can be in an excited state or a ground state. And whether it's an excited state or a ground state could be the 0 or 1 of the bit. You can have current flowing in a superconductor, a little superconducting circuit. And the current could, for instance, be flowing clockwise or counterclockwise. Clockwise could be a 1, counterclockwise could be a 0. You say, how could it be flowing both at the same time? Well, remember, this is quantum mechanics. You can't say whether it's flowing clockwise or counterclockwise. Finally, every electron on Earth carries a little bit of magnetic north-south. And it's not much, so that if you don't actually actively try to measure it, and it's kind of hard to measure it, the universe kind of leaves it alone. It just kind of freely spins. But if you could use that to orient the 0 or 1, then you tend not to screw with it until you actively put on a magnetic field that flips it. So that's a good candidate also. So lots of different labs have lots of different candidates, and every lab has their favorite candidate. And to be honest, it tends to be what they were working on already before quantum computing got invented. They say, mine's a good system for that. If you're an atom guy, like this Dave Wineland, Nobel laureate, who works with atoms, and said, you know what? I think my atoms are exactly what the doctor ordered here. But the spin guys think, oh no, I think my electrons are exactly what the doctor ordered. The superconducting guys say, this is exactly what the doctor ordered. My system is. And so far what's happened in the US and in Europe and in China and in the rest of the world is a lot of these approaches are competing with each other. Nobody has decided, and correctly I would add my own opinion, has down-selected and said, that one's stupid, don't work on that one. Because who knows? Nobody knows. It's a brand new problem. What's the right system in which to do this? Well, let's let a lot of people try their different problems and see who can get the most bits going and who can have them stay coherent for the longest amount of time. That's what's happening now. That's a snapshot of 2020, is that there are labs with atoms, superconductors, spins, and they're all kind of competing with each other to make this thing work. Here's one of the superconducting ones. This little loop right here contains two of what are called Josephson junctions. They're two little breaks in the superconductor, and you have to send all the signals in and out, and they use this superconducting grid to do it. This is an electron micrograph. It's a very impressive thing. But even more impressive is the work that came out of, I'm going to skip more quickly. Well, let me tell you what this is. Here's the issue. I sneaked a word in, and I want to bust myself for sneaking it in without saying what I meant. When we were talking about the bits over here, and I said, well, we can't measure. And then I said, you can't even accidentally measure. Like, I can't accidentally find out whether you're in a 0 or a 1 state. Let's say you interact slightly differently with that cushion that you're sitting on, depending on whether you're a 0 or a 1. Maybe you're a tiny bit heavier when you're a 1 than you are a 0. The cushion will know. The cushion will know whether you're a 0 or a 1. And if the cushion knows, it's going to tell the cushion next to it, and pretty soon everyone's going to know. And then you're not quantum mechanical anymore. You've been measured. Not on purpose, but accidentally, when you thought you were protecting your information, the cushion measured you, and pretty soon everybody knew. That's what happens. That's why these machines don't work that well. That's why when you put something in a superposition of the two states, when you make it a 0 and a 1 at the same time, you only have a few tens of microseconds before the quantum mechanics goes away. It goes away accidentally because the universe accidentally measures it. That's important because that's why we don't have these machines right now. The ideas are all there, the technologies are there. We're trying to prevent the cushion from measuring whether you're a 0 or a 1, and we don't know how to do it very well. So we can only get a few hundreds or a few thousands of operations as fast as we can operate before the quantum mechanics is gone. Now, this was pushed to its logical limit last year, 2019, a very important year for quantum computing, because Google, in a group run by John Martinez at Google, pushed as far as they could with this thing, up to 53 qubits interconnected with each other in various kinds of geometries, and found that they could just achieve, after a few tens of thousands of cycles, where all the fidelity had crashed and they'd lost most of the information because it was too long compared, but it was long enough to perform a calculation that a classical computer can't perform. They outperformed a classical computer. What was the problem? Forget about it. You don't want to know. It was a stupid problem, by their own admission. It was a problem that nobody cares what the answer to the problem is. But it was a problem that a classical machine can't solve as fast as their quantum machine could. That was a first, and that was 2019. Next, it would be nice to get it to be a little bit bigger. Next, after that, it would be nice to have it work on a problem that was a practical problem. But boy, it's important to demonstrate that you can solve a problem faster than a classical computer can solve it. And that was 2019. So hats off to John Martinez for doing that. For the end of my talk, and I probably have about 10 minutes left or something like that, I'm going to change the subject to the topic of this week's conference. And I want to draw my inspiration from this many thousand-year-old technology of storing information in topology. Remember the title that he said you weren't expected to know every word. Topology is a branch of mathematics that is concerned with the shape of objects without any interest in their details. If it can be deformed, so, like I lost 20 pounds, I'm still me. Even if I became a sphere, I'd still be me. But if there's something like a rope that has a knot tied in it, that's not the same as a rope without a knot tied in it. In fact, every one of you knows that a rope with a knot tied in it is different than a rope without a knot tied in it, because you every day take out your headphone jack cord, and it's all wrinkled up, and you'd say the same thing to yourself that every other person in the world says, which is, I wonder, if I just pull on the end of it, will it come out straight or will it be tied in a knot? And the answer is, it's either one or the other. The answer is not maybe. Try it sometime. Next time you take out your headphones, just pull on the end of the cord. It will either be in a knot or it won't. They are topologically distinct states. It doesn't matter whether you wrinkle it all up. It doesn't matter whether you hold it in a ball. Just pull it and find out. It won't change. That was the basis for storing numerical information back in Mesoamerica. And in fact, it was even a system that used the decimal system, and they would tie the knots in this way. And why do we know that now? Because the things are still sitting in the ground, and they still have knots tied on them. All the parchment is gone, everything else is gone, but the knots are still there. Those knots don't come out. In fact, the first computers were in the business of tying things in knots. They were weaving machines. Here's a picture of the computer. It actually used punch cards to determine the rows up and down. Let's call that the first computer. And what was the output of the computer? It was weaving. It was putting fabric through loops and knots, just like the fabric of my shirt. And when you pull on it, the knot doesn't come out. It's woven in. The memory of the history of which thread went around which thread is embedded in the time history of my cloth. And that, in fact, was the first computer. Now let's bring this to quantum mechanics. Because what we said in quantum mechanics was, if your state is measured, you're not quantum anymore. Maybe we can hide the state in such a way that the cushion won't measure it. The cushion won't know whether it's quantum mechanics, whether it's in a knot. So I drew this picture here, and I said, if you look at the rope, if you measure the rope somewhere locally, that no local measurement can see whether this rope has a knot in it. You have to kind of step back and see who goes through what in order to see whether there's a knot tied in it. Therefore, any information that's encoded in knots will not be crashed by a measurement that only operates locally, which is how most measurements operate. They operate on a spot on the material. If that spot on the material weighs you, measures your qubit, tells you whether you're a 0 or 1, quantum's gone. So hide the information in a knot because a local measurement can't see it. Here's the only problem. The only problem is we need particles that you can tie in knots, and they don't exist. The memory of those particles doesn't exist. Well, that's okay. Let's invent them and then tie them in knots. So it's kind of a two-step process. Our friend Mike Friedman from Microsoft was one of the early developers, along with his colleagues, particularly Alexei Kitaev, who was one of the inventors of this, of a branch of quantum computing called topological quantum computing. And he mentions right in the abstract that the chief advantage of this, it was called anyonic, forget that, topological quantum computing would be physical error correction. The errors that are encoded aren't susceptible to being measured. It was just an idea. He's a mathematician. I mean, he's not even a theoretical physicist. He's a step removed from that. But it didn't take long for the theoretical physicists to realize that if you had such particles that you could tie in knots, they're not worrying at the moment about what those particles are or where to get them. They're saying if you had a particle that you could tie in a knot, you could make a computer that only used the tying in knots as the way to process information. So you could do an entire general computer just using this knot business and encode information in knots. Now all we have to do is find the particles that do it. Now this is such an important and novel idea, the subject of this conference this week, of all these physicists out here who are studying materials that have this property, that they have a topological character, that their excitations can be tied in knots, that this was the recipient of the 2016 Nobel Prize in Physics. And I'll just read to you about these topologically distinct materials. Topological insulators, topological superconductors, topological metals are now being talked about. These are examples of areas which, over the last decade, have defined frontline research in condensed matter physics. not least because of the hope that topological material will be useful for a new generation of electronics and superconductors, or in future quantum computers. So let's try to make one. Let's try to tie particles in knots. In 2010, 10 years after the original ideas of topological quantum computing were first put on the table, one particular idea emerged for creating excitations that would have the property that if you wrapped one around the other, it would remember. And it involved objects that had really never been combined before, probably. It involved a superconductor, a material that conducts electricity without any dissipation. It involved a one-dimensional wire. By one dimension, I mean something in particular. I mean that along the length of the wire, the electrons can move. But transverse to the direction, in the narrow directions of the wire, they're in their lowest quantum mechanical state. Just like in a hydrogen atom. The hydrogen atom is in its lowest state. So imagine something that's in its lowest state that way, in its lowest state that way. But this way, it's free to run. So it's like a long, skinny hydrogen atom. That's a one-dimensional wire. And the third ingredient is an external magnetic field. You put those three ingredients together, the theoreticians tell us that there will be balls at the two ends. What happens when you wrap them around each other? Well, only one of two things can happen. When you bring them together, they will either become an electron or they'll become nothing. Very simple, but wrappable, topological. You can wrap one around each other and change who's got the electron. It becomes a game of who's got the electron, meaning when you take a new pair and put them together, do they become an electron or do they become vacuum? That was the idea. How do you do it? Well, if you wrap these two around each other and this pair had the electron at the beginning and this pair didn't, and then you swap partners, well, who's got the electron at the end? Well, you can do that by moving these things around. If I want to swap where they are, I have to step into the aisle, bring this one down, step around the other side, and I've effectively made this change of swap of the who's got the electron game. You know, I have to say that I had no intuition for this who's got the electron Majorana problem until I was in Estes Park, Colorado, kind of a tourist trap kind of town. Well, I'm from Sonoma, so I can say something's a tourist trap. And we're in Aspen, so we can say it too. But there I was in Estes Park, and I saw does anyone know what that is? Yeah, it says up there, sorry, that's a stupid question. It's saltwater taffy. It's a taffy puller. And I was looking at this thing in the window, and I liked the way that it matched the window frames also. And I saw a pair of Majoranas and another pair of Majoranas, and I was just watching them switch partners, that the pair would make a partner, and then the next pair would make a partner, and they were trading off who was partnered with who, and that each branch would then exchange who was the partner. And the question is, could you take those Majorana pairs at the ends, make a whole computer out of those, where each time they swapped not who's got the electron, but who would have the electron if you brought the two together and promise you'll never put them together. That's the idea of these Majorana computers. We know how to make the wires. We know theoretically what to look for if those red balls are there. What do we look for? We look for a peak at zero energy after you put the magnetic field on. Remember, you needed superconductivity, the one-dimensional wire, and the magnetic field. When you have no magnetic field, there's nothing at zero. You turn on a magnetic field, there's a big bump at zero. Look for the bump at zero. This was 2011, the year after the idea came out, and it didn't take very long for my buddy Leo Kouwenhoven here, Leo Kouwenhoven and his group at Delft University, to make the device. There's the wire, there's the superconductor, there's where you put the electrons in, and there's this crazy peak right at zero when you turn on the magnetic field up to the right limit, calling the paper Signatures of Majorana Fermions in Hybrid Superconductor, Semiconductor, Nanowire Devices. Now at least I dare say the title makes sense. Very soon after that, go back. Very soon after that, Leonid Rockinson and his team at Purdue generated another signature, the disappearance of a peak, another prediction of the existence of these Majoranas, and pretty soon, 2012 became the year that these first signatures were seen. 2 years after that, my lab in Copenhagen developed the next level of technology, which is to grow the superconductor and the semiconductor together. Instead of slapping them together as a sandwich, grow them. Here's the surprising result. The semiconductor and the superconductor grow very nicely together. So for my lab, a grown semiconductor, and now the theory, turned on its side so it matches the data, starts to look awfully like what the red ball prediction looks like. We're pretty much getting there. Now, something's interesting about that, which is that this guy Couwenhoven and I, who've been friends and competitors for 30 years now, he introduced me on this very stage 10 years ago, and the computer didn't work. It was an interesting hour. Anyway, we got through it, but it was then almost spooky when I came into Aspen yesterday and saw not only is there a Couwenhoven building on the corner, but that Marcus seems to have invaded it. And I thought this is a really special town for topological quantum computing, and that now the whole thing in Aspen sort of makes some sense. So let's make our first qubit. The first qubit, and I realize I got to stop. 2 minutes, he said to me. The first qubit is going to look a lot like this taffy puller, except it's going to be in a straight line because I'm going to use one wire. And I'm going to be opening and closing the doors instead of moving them around in circles to catch the handoff. I'm going to use the semiconductor property. They really aren't doors. They're drawn here by our theoretician friends, Jason Alisea and David Asen, to opening and closing doors. But you know that you can open and close a gate on a semiconductor. That's what semiconductors do. You put a voltage on there and it shuts the door. You take the voltage off and it opens the door. That's classical semiconductor physics. And these things are indeed made out of semiconductors with superconductors on them. And what this theoretical paper shows is, with some judicious opening and closing of the doors, and what I mean by that is the opening and closing of the voltages that open the doors, I can play who's got the electron when I bring them back together, and that's the idea of the Majorana-based quantum computing. The Majoranas are these half electrons that either fuse to vacuum or electron at the end. The devices themselves start to become rather complicated because not only do I have to have the nanowire with the grown superconductor and the ends where I do the measurement, but I have to put all those doors on so that I can operate the thing. So one little tiny topological object starts to get kind of complicated. That thing sits on a chip. That chip is on a conventional electronic carrier. That carrier sits inside of a big hunk of metal. That big hunk of metal sits at the bottom of a refrigerator, which then has to take the thing to 1/10 of a degree above absolute zero, where all of this experiment has to take place. Why absolute zero? Because I don't want the cushion to shrink when I have that qubit. Even though it's topological, it's still susceptible to inadvertent measurement. That thing sits inside of a refrigerator, which is inside of my laboratory, and you know this must be Denmark, because where else would you find a laboratory with hardwood floors? Now, things do get more complicated, and to build the kind of machines that we need in order to solve that nitrogenase molecule, we're going to have to put a lot of red balls on a lot of sticks and put this whole thing inside of one computer. The big breakthrough came, and I think that the author of this work is here in the room with us from a couple of groups, including Mike Manford's laboratory at Purdue University, is to extend this wire idea to 2 dimensions. Now, 2 dimensions is a lot more than just one, because once you have something in 2 dimensions, then you can define the wires lithographically, not by making one wire and laying it down. Imagine what a pain in the neck. Try building a whole computer out of these little stupid wires. Instead, you have to lithographically define all of the wires. And when you have a 2-dimensional substrate, you can pattern 1 or 100 or 1 million using the same lithographic process. That's a breakthrough, when you can suddenly pattern wires. And so when we see this level coming down, hitting zero, and making a Majorana, not in a wire that's grown as a wire, but in a wire that is patterned as a wire, the next breakthrough had come through. The final thing that I want to say is this. We're going to need 1 million qubits just in order to get that 100-qubit system. Why? Because I need to build in redundancy. There's too much measurement that goes on inadvertently, but I can get rid of some of that measurement with redundancy. But the redundancy factor is pretty daunting. Like, I might need 1,000 qubits or 10,000 qubits for every logical qubit that does what it's supposed to do. So that overhead factor means my refrigerators start to look a little bit complicated when I have to run all of those wires down to the bottom. In fact, I hope what you're thinking to yourself is, that's no way to run a business. That's not going to get us to 1 million things down at the bottom of a 0.1 Kelvin refrigerator, running everything down through coaxial lines from room temperature. The engineer in here must be horrified. So one of the challenges, which you might find mundane, but which is absolutely central to the improvement of the technology, I wanted to show you what the kind of numbers are. So in the back of this paper, this one that I showed you before, in the back of the paper, they give the numbers. How many total physical qubits? Oh, look, everybody's very happy. How many logical qubits? Logical qubits, 100, 110, 109. No problem. Oh, yeah? Well, when you get down to counting the total number of physical qubits, depending on how good each individual qubit is, maybe it's only 10 to the 5 or 10 to the 6, or maybe it's 10 to the 11, or maybe it's 10 to the 9 qubits. So you better have an idea in mind beyond running those wires down from room temperature to the bottom of the cryostat. But actually, it's okay, because we have chips in our pocket with 1 billion working transistors. The only problem is you got to get them down to the bottom of the refrigerator and have that chip working at millikelvin temperatures, not coming down from above. So here's the first one of a cryogenic control system that functions at the lowest temperatures. These will all have to replace the classical control, the opening and closing of all of the gates when we're finished. This, I think, is the end of my presentation. I've covered a range from the Bohr-Einstein debates through to cryogenic control of Majorana fermions. It's been a wild ride. Thanks for coming along with me.
Wow. This is one time I feel really a villain to stop the show. But before Patty comes up to kill me, I think we can take a couple of questions.
Yes, our engineer.
The engineer would like to know when that quantum computer is going to actually be able to do something useful.
Can you repeat the question?
Yeah. Well, if generating funding is useful, it's already happened. I want to push back on the form of the question in a way which I think you'll accept, which is every year something new happens. And of course, the year of 2018, they weren't asking the question the way you asked. They said, well, when are we going to have a quantum computer that could do something, that a regular computer can't do? It was 2019. Now you ask, when is it going to do something useful? Well, what if it's a little bit useful? What if we kind of knew the answer anyway, like that factoring problem? It's going to just get better and better every year, and I don't think looking back, just like with conventional computer technology, there is no conversation like, when did the laptop happen? You remember, there were like these gigantic, crappy laptops at the beginning, and then they got a little bit better. And then a few years later, for those of us old enough to remember, they got a color screen, and then they got a little bit lighter, and then the battery lasted a little bit longer. That's what's going to happen with quantum computing. It's going to get better every year so that you won't even notice when all of a sudden they're solving problems that they couldn't solve before. And so I think that I want to say that this is more about evolution than revolution, and that the little games that we're playing right now are part of a long arc that I think will take the next 50 years. And at the end of that 50 years, we'll have something that we will not only not recognize how computers work, but we won't be able to distinguish the incremental steps. That's my long answer to your question.
So can I ask it in the fusion energy sense of the word? When is it going to break even? When am I not going to have government money pouring into it to keep it alive?
Oh!
When am I going to be able to?
Well, Microsoft, as an example, I work for Microsoft in addition to working at the University of Copenhagen, and there's 140 people working in their quantum program, and none of them is supported by the US government. They're all supported by Microsoft. Because Microsoft is nice? No. Because Microsoft thinks that this is an important thing for the future of technology. Intel, IBM, Google, Airbus, all the same thing. They're all paying to play. Oh, you mean when will we be able to do something that we can't do with a conventional computer?
When will, for example, take airline scheduling, take traveling salesmen, any kind of big problem like that?
Yeah, well, you can go read that. In fact, already Volkswagen has purchased optimal solutions to, I think, truck routing that have been solved on a small IBM processor or something like that. Now, could it have not been done another way? No. It could have been done another way. So it wasn't the traveling salesman problem. Now, the interesting thing about the traveling salesman problem is that it's an NP-complete problem. It's in a class of problems. I'm not an expert at this, but this one I happen to know. That's a hard problem. That's a problem that's in a class of problems that probably a gate-based quantum computer will not solve. It's an optimization problem that has many, many nearly optimal solutions. And I can ask you as an engineer, do you want the best route, or do you want a darn good one fast? Probably the latter. And so that class of problems, where there are an exponentially many solutions and you want a pretty good one, not the very best one, that's a different kind of problem. And there are quantum computer companies called D-Wave that are already taking on optimization problems of exactly that ilk, including traveling salesman-like problems, NP-complete hard problems. And what's interesting about that problem is it is not known on this very day whether or not a quantum computer will ever outperform a classical computer on optimization problems. It is not known. I mean, not even known theoretically. It's not, forget about the question of when will we have a machine. The theoretical answer to the question of will it in principle outperform a classical machine is not known. So we're kind of in our infancy, but it's good. It's a good time to be alive. We get to not know the answer to a lot of things. Thanks for coming along with me.